All right, so now we're going to say a little bit more about how you go about actually computing this solution to the trust region subproblem. Okay. Okay. So again, it's like you have to compute sort of the arg minimizer of the following. And the function you're minimizing is this quadratic model of the cost function. Okay, and then this is what I call the local model, which is m hat xk. All right, so there's sort of two basic approaches. Okay, so the first one is to sort of compute nearly exact solutions of the subproblem. The second approach is to compute an approximate solution using a computationally simple iteration that at least decreases the cost by as much as the cost obtained at the Cauchy point. So there's some notion of sufficient descent, if you recall, when we were discussing the global convergence properties of line search methods, and that involves the notion of this Cauchy point. Okay, so let's define it's like the Cauchy point. Okay, so for the trust region problem, if you assume that the gradient at of f at the iterate, the current iterate, is not equal to 0, right? Then the Cauchy point, the following, is the solution of this one-dimensional problem. Okay, so it's the arg minimizer of m hat xk in a particular direction, where this is the some negative tau times the gradient of f at xk. Okay, and tau is greater than 0, and the norm of this is less than equal to delta k. Okay, so this is essentially just a line search method, right? So you're searching in a direction, it's like which is in the negative of the gradient direction, and you're looking for points along this line, it's like up to a distance of less than or equal to delta k, so you stay within the trust region method. Okay, so this reduces to the classical definition of the Cauchy point when the manifold is Rn, okay, and the Cauchy decrease is given by just the difference between the m hat, so this is the model at 0x, which is the initial point, minus m hat xk at the Cauchy point. Okay, so we'll talk about this first method before providing a sort of second approach. It's like which is based on essentially conjugate gradient. Okay, so again, there's some. Yeah, so the second one, it's like involves again sort of a computationally efficient method. It's like which does at least as well as the Cauchy point. It's like but potentially better. Okay. All right. Let me just erase up to the definition of the Cauchy point. Okay, so I'm going to compute the nearly exact solution. So again, I'm trying to compute nearly exact solution of the trust region subproblem, okay, which again involves finding the minimizer of of this quadratic model. It's like of the cost function expanded about the point xk, but within a ball radius delta k around xk. That's sort of intuitively what's happening here. Okay, all right. So let's state a proposition which will be helpful. So the vector eta star is a global solution of the trust region subproblem if and only if, right, there exists a scalar mu greater than or equal to 0 such that the following is true. The following conditions hold. Okay, so the first one is that hk plus mu times the identity, right, eta star is equal to minus the gradient of f xk, right? This is a little bit like sort of the Newton equation, but modified slightly, right? And in particular, if you recall, it's like the modification was so that this shift of hk, it's like by mu times the identity, is positive semi-definite, okay? So the second one is that mu times delta k minus the norm of this eta star, right, is equal to 0. So the third condition is that hk plus mu times the identity is positive semi-definite. If you recall, it's like this positive semi-definiteness condition was necessary for this eta star, it's like to be gradient related, right? Well, not necessary, but it allowed us to prove that this was gradient related. Okay, and then the last one is that this norm of this is less than or equal to delta k, which of course is necessary because this is one of the constraints. It's like in the trust region subproblem. Okay. So anyway, so this is just a proposition. It's like, and nice thing about it is that these conditions are sort of if and only if, right? So all these things have to hold. It's like for this to be a global solution of the trust region subproblem. So this naturally leads to using some of these conditions then as a way of constructing a solution of the trust region problem. Okay, so let's see how you do that. Okay, so you sort of do one of two things. So you can use this it's like for computing the solution of the subproblem. Okay, so you can either solve the system with mu equals to 0, or we can define the following, right? Eta as a function of mu as minus, so this is defined to be minus hk plus mu times the identity inverse applied to the gradient of f at xk. All right. Okay, so there's, I mean, there are two possibilities, right? I mean, two general possibilities, that mu is 0 or that mu is not 0. And if mu is not 0, we can compute this as a function of mu, right? And then we adjust mu to achieve the condition that the norm of eta as a function of mu is equal to delta k. Okay, so this is like a one parameter search. It's like where the parameter is mu. Okay, and you know, there are several methods which are based on using this kind of general approach. Okay, so so let me stop here for now. It's like, and the next thing we'll talk about is how to improve on the Cauchy point, which is sort of this other class of methods for doing the sort of the inner iterations. So let me just stop here for now.